AI is everywhere these days, isn't it?
Yeah, it really feels like it's impossible to escape.
Especially with chatbots. ChatGPT, Claude, Gemini, Llama, they're all over the news.
And people are really starting to use them. I mean, not just talking about them, but actually integrating them into their work.
Exactly. But for this deep dive, we're going beyond the hype.
Right, we're going deeper.
We want to understand how these large language models,
LLMs.
LLMs, yeah, how they're actually built, like what's going on under the hood.
It's like getting a backstage pass to the world of AI.
And the backstage pass we have for this deep dive is a transcript from a Stanford CS229 lecture, all about the construction of LLMs.
It's a fantastic resource, really packed with information.
So our mission, so to speak, is to unpack this lecture,
Pull out the core components, the methodologies,
the essential building blocks of these LLMs.
and of course, explain it all in a way that makes sense.
Yeah, even if you're not a computer science PhD.
Right, no matter your background, we're going to break it down for you.
Okay, so looking at this lecture transcript, they start by outlining 5 key elements involved in training these massive models.
Right, 5 key ingredients.
First, there's the architecture.
You know, the blueprint of the neural network.
With things like transformers, which, I have to admit, even for someone who follows this stuff, transformers are still a bit mind-boggling to me.
They're incredibly complex, yeah, but really effective for processing language.
Right. But we're not going to go too deep into the architecture in this deep dive. I think there are tons of resources out there if people want to get into the nitty-gritty of how transformers work.
Yeah, and to be honest, what we found in the lecture is that the architecture, while important, it's not the only piece of the puzzle.
Okay, so what else is there?
Well, there's the training loss and the training algorithm. This is basically how the model learns.
Right, kind of like how we learn from our mistakes.
Right, exactly. Then there's the data itself. Huge amounts of it. It's the fuel that powers these AI systems.
Makes sense. You can't learn without something to learn from.
And then there's evaluation, which is all about measuring how well the model is doing. How much has it actually learned?
Right, like giving it a test.
Yeah, exactly. And finally, there are the systems.
The infrastructure.
The hardware, the software, the optimization techniques, all the things that make it possible to actually train these massive models.
Right, because we're talking about models with billions, even trillions of parameters. It's mind-boggling the amount of computing power that takes.
Absolutely. But that's a conversation for later when we dive into the systems aspect. What I found really interesting in the lecture is this contrast they drew between academia and industry.
Oh, interesting. How so?
Well, in academia, there's a lot of emphasis on the architecture and the training algorithms.
Right, pushing the boundaries of what's possible.
Exactly. It's about exploring new ideas, coming up with new models, and testing them rigorously.
So, theoretical breakthroughs.
Yeah. But when you move to industry, the focus often shifts.
To what?
Data, evaluation, and systems.
Okay, so the more practical side of things.
Exactly. In industry, it's all about building models that actually work in the real world, that can be deployed, that can be used to solve real problems.
And that means having good data to train them on.
Tons of it.
Having robust ways to evaluate how well they're doing.
Right.
And having the infrastructure to support it all.
You got it. So for our deep dive today, we're going to lean a bit more towards that practical side. We'll definitely touch on the architecture and the algorithms, but we'll spend more time exploring the data, the evaluation, and the systems.
Makes sense.
Yeah.
So with that in mind, the lecture goes on to discuss the 2 major phases in LLM development.
Pre-training and post-training.
Right. So let's start with pre-training. What exactly is happening in this phase?
Pre-training is all about language modeling. It's the stage where the model learns to understand and generate human language.
So basically you feed it a ton of text.
And I mean a ton of text. We're talking about massive data sets scraped from the internet, books, code, you name it.
And the model just absorbs all of that.
It does. It learns the patterns, the structure, the nuances of language.
And this is where models like GPT-3 and GPT-2 come from.
Exactly. Those are prime examples of models that have been pre-trained on vast amounts of data. The goal is to create a model that can, in a sense, model all of the internet.
Wow. Okay, so once you have this pre-trained model, what happens next?
That's where post-training comes in.
Right, the second phase.
And this is where things have gotten really interesting, especially with the rise of models like ChatGPT.
So what's the focus in post-training?
Taking those pre-trained models and turning them into AI assistants.
Okay, so making them actually useful.
Exactly. Teaching them to follow instructions, to be helpful, to exhibit specific behaviors. It's about taking all that raw knowledge and refining it into something that can be applied in the real world.
This is starting to paint a clearer picture of the whole process.
Good. So let's unpack pre-training a bit more. The lecture goes into some detail about the task of pre-training, which, as we said, is language modeling.
Right, but what does that actually mean?
At its core, a language model is a probability distribution.
Uh-oh. Math.
Don't worry, it's not too complicated. What it means is that the model learns to assign a probability to any sequence of words. So if we take the sentence, "The mouse ate the cheese,"
Classic.
the language model will assign a probability to how likely that sequence of words is to occur in human language.
So a higher probability means it's a more common, more natural-sounding sentence.
Exactly. And the lecture gives some great contrasting examples.
Yeah, I remember seeing those.
They're like the mouse at cheese.
Grammatically incorrect.
So the model should give that a lower probability. Or the cheese ate the mouse.
Which is grammatically correct, but doesn't make much sense semantically.
Right. The world just doesn't work that way. So a good language model should also assign a lower probability to that sentence.
Because it's less likely to be uttered by a human.
Precisely. It's about learning the statistical patterns of language. And because these models are trained to predict what word comes next in a sequence, they fall into the category of generative models.
Generative models, what does that mean?
It means they can be used to generate new text. Once the model has learned this probability distribution, you can sample from it to create entirely new sentences.
So that's how you get those AI-generated stories and poems and things.
Exactly. Now, the most common type of language model in use today is the autoregressive language model.
Autoregressive.
Oh,
Sounds kind of intimidating.
it's actually a pretty simple concept. It just means that the model predicts the next word based on all the words that came before it.
Okay, so it's like building a sentence one word at a time,
Yeah, and the lecture mentions the chain rule of probability here.
which is,
It's a way to calculate the probability of a sequence of events. In this case, the events are the individual words in a sentence.
so you calculate the probability of the first word, then the probability of the second word given the first word, and the probability of the third word given the first two words, and so on.
Exactly. You're essentially breaking down the probability of the entire sentence into a series of conditional probabilities.
But this must take a long time to generate longer pieces of text, right?
It does, and the lecture points that out as a limitation. The longer the sequence, the slower the generation process. But it's a very effective approach for capturing the dependencies in language.
So let's get a bit more concrete. Let's say we have the beginning of a sentence. She likely prefers. What are the steps the model takes to predict the next word?
The first step is tokenization.
Tokenization. We talked about that a bit earlier.
Right. It's the process of breaking down text into smaller units called tokens.
So instead of working with whole words, you work with these tokens.
Exactly. And each token is assigned a unique numerical ID.
Okay, so she might get ID 1, likely might get ID 2, and prefers might get ID 3.
Right. And those numerical IDs are what the model actually works with.
So what happens next?
These IDs are fed into the LLM, which then outputs a probability distribution over all the possible next tokens.
So for every token the model knows, it calculates how likely it is to be the next word in the sequence.
Exactly. So in our example, the token for the word dogs might have a very high probability.
Because she likely prefers dogs is a plausible sentence.
Right. But there's also a chance it could be cats, coffee, or any number of other words.
Each with its own calculated probability.
Precisely.
And what happens when the model is actually generating text?
During text generation, we typically sample from this probability distribution.
So you pick the most likely token.
Not necessarily. You can introduce randomness to make the generated text more diverse and interesting.
Okay, so you might pick dogs most of the time, but sometimes you might pick cats or coffee just to mix things up.
Exactly. And once you have the ID of the next token, you detokenize it.
Meaning you convert it back into an actual word.
Right. So if the chosen token is ID 4, which corresponds to the word dogs, you get the sentence, "She likely prefers dogs."
That makes sense. But the lecture emphasizes that this sampling and detokenization is mainly for inference when you're using the model to generate text.
Right. During training, the process is a bit different.
How so?
During training, we're not trying to generate text, we're trying to make the model accurately predict the next token in the training data.
So if the actual sentence in the training data was, "She likely prefers dogs," the model should ideally assign the highest probability to the dogs token.
Exactly. And we use a measure called cross-entropy loss to compare the model's predicted probability distribution with the actual next token.
So the loss tells us how wrong the model was.
Yeah. and we adjust the model's weights to minimize this loss.
Which essentially means making the training text as probable as possible to the model.
Precisely. The lecture highlights that minimizing this loss is equivalent to maximizing the log likelihood of the text.
So it's a continuous process of the model trying to get better and better at predicting the next token.
Exactly. And as it gets better, its language modeling abilities improve.
Now let's go back to tokenization.
Right, back to the beginning.
The lecture really emphasizes the importance of tokenizers,
They are absolutely crucial.
but they often get overlooked.
They do. People tend to focus on the model architecture, the training algorithms, but the tokenizer is the foundation.
So why are tokenizers so important?
Well, for a couple of reasons. Firstly, they're more general than just words.
Okay, how so?
Think about typos.
Yeah, people make typos all the time.
If your vocabulary only consists of correctly spelled words, a misspelled word won't have a corresponding token.
And the model will be confused.
Exactly.
So tokenizers can handle those variations.
They can. They can be designed to break down words into smaller units, like characters or subwords, which allows them to represent typos and other unusual spellings.
Interesting. What's the second reason?
Efficiency. You might think, why not just break everything down into individual characters?
Which seems logical at first.
But the problem is that it would result in very long sequences.
Yeah, even a short sentence would have a ton of characters.
And as we discussed, the computational cost of processing these sequences increases with their length.
So you want to find a balance.
Exactly. You want tokens that are meaningful, but also short enough to be computationally efficient. The lecture mentions an average token length of 3-4 letters as a good target.
Okay, makes sense. Now, there are different methods for tokenization, right?
There are, and one common method is byte pair encoding, or BPE.
BPE, how does that work?
It's a pretty clever algorithm. It starts with a huge text corpus.
All the data you're going to use to train the model.
Right. And initially, every single character is treated as a separate token.
So if your corpus has the word cat, you start with the tokens C, A, and T.
Exactly. Then the algorithm iteratively scans the text and finds the most frequent pair of adjacent tokens.
So if the sequence K appears very often, it gets merged into a new token.
Precisely. And this process is repeated many times.
Merging the most frequent pairs until you reach a desired vocabulary size.
Exactly. And the lecture gives a nice example with the words to, top, to, token, and towing.
Yeah, I remember that.
Initially, all the characters are separate tokens, but then T and O get merged into two because they appear together so often.
And then 2 and K might get merged into tuk-tuk.
Right, and so on. Until you end up with a vocabulary of tokens that captures the most common sequences in your data.
So a real-world tokenizer might break down the word tokenizer into the tokens token and izer.
Exactly, because token is a common sequence that's likely been learned by the BPE algorithm.
What about spaces and punctuation?
That's a good question. Often there's a pre-tokenization step where spaces and punctuation are handled separately.
So you might break down the sentence, hello world, into the tokens hello, ara world. And
Right, and then the BPE algorithm would be applied to those tokens.
so you wouldn't get weird merges like O or D.
Exactly. But in theory, you could skip pre-tokenization and treat everything as a character.
And let the BPE algorithm figure it out.
Right. But that might be less efficient. Now, another question that came up was whether you lose the ability to represent the original smaller tokens when you merge them into larger ones.
Right, because if you merge C, A, and T into cat, can you still represent those individual letters?
You can. The original tokens are usually retained in the vocabulary.
Oh, okay.
So if the model encounters a typo, like cat, the tokenizer can still break it down into C, A, and T.
Even though cat isn't a token in the vocabulary.
Right. It gives the model more flexibility.
That makes sense.
Hmm.
And each of these tokens, whether it's a single character, a subword, or a whole word, gets its own unique ID.
Right.
And then the model learns to associate these IDs with their meanings,
Exactly. But it can get a bit tricky. Like the lecture gives the example of the word bank.
which can have multiple meanings.
Right. Like a financial institution or the side of a river.
So how does the model know which meaning is intended?
It uses context.
The surrounding words.
Exactly. So even though both meanings of bank might be represented by the same token ID, the model can use the other words in the sentence to disambiguate.
That's pretty amazing.
It is. It's one of the things that makes LLMs so powerful. Now, the lecture also talks about some of the limitations of current tokenizers.
Right, because they're not perfect.
They're not. One example is mathematics.
Oh, interesting.
Current tokenizers don't really handle math very well. They tend to treat numbers as single, indivisible tokens.
So if you have the number 327, it might get its own token ID.
Right. And that means the model doesn't really understand the relationship between the digits.
It just sees it as a random symbol,
Pretty much.
which can be a problem for tasks that involve mathematical reasoning.
Absolutely.
What else?
Well, another issue is the quadratic scaling problem.
Quadratic scaling.
It means that the computational cost increases quadratically with the length of the input sequence.
So as the sequences get longer, the cost goes up dramatically.
Exactly. And this is a major bottleneck for current models.
So what's the solution?
The lecture suggests that if future architectures can overcome this scaling problem.
We might see a shift towards character level or even byte level tokenization.
Right. Because with those approaches, the tokens are much smaller, which would reduce the sequence length.
Interesting. It seems like tokenization itself is still an area of active research.
It definitely is. It's a crucial component of LLM development, and there's still a lot of room for improvement.
Okay, so we've covered the task of pre-training, the loss function, and the importance of tokenization. Now, how do we know if our model is actually learning anything during pre-training?
That's where evaluation comes in.
Right, you have to test it.
Exactly. And one traditional metric for evaluating language models is perplexity.
Perplexity. I've heard that term before, but I'm not sure I fully understand it.
It basically measures how surprised the model is by the text it encounters.
Surprise!
Yeah. The idea is that a good language model should be able to predict the next word with high accuracy.
So if it's constantly surprised by the next word, it means it's not doing a good job.
Exactly. Lower perplexity means better performance.
Makes sense.
And perplexity is calculated by exponentiating the average per token loss.
So the lower the loss, the lower the perplexity.
Right. And taking the average makes the score independent of the sequence length.
So you can compare models trained on different data sets.
Precisely.
And the lecture mentions that perplexity has improved significantly over the years.
It has. The models are getting better and better at predicting the next word.
But perplexity is not the only evaluation metric, right?
It's not. And in fact, it's not as widely used for benchmarking as it used to be.
Why is that?
Well, the lecture points out a couple of limitations. First, perplexity depends on the tokenizer.
Ibra tokenizers can lead to different scores.
Exactly. So it's hard to compare models directly if they use different tokenizers.
What's the second limitation?
It also depends on the dataset. A model might have low perplexity on one dataset but high perplexity on another.
Okay, so it's not a perfect measure.
It's not, but it's still useful during development.
Right, for tracking the progress of your own model.
Exactly. But for benchmarking and comparing different models, there's been a shift towards using other metrics.
Like what?
Classical NLP benchmarks.
NLP benchmarks.
Natural language processing benchmarks. These are tasks that test the model's ability to understand and process language.
Like what? Give me an example.
Sure. One common benchmark is question answering.
Like give the model a question and see if it can answer it correctly.
Exactly. And this is a useful benchmark because it's easy to evaluate.
Right. You know the correct answer, so you can just see if the model gets it right.
And the lecture mentions aggregate benchmarks like Asia LM and the Hugging Face Open LLM leaderboard.
Which compiles results across multiple benchmarks.
Exactly. They give you a more comprehensive view of how well a model performs on different tasks.
And one specific benchmark they highlight is MMLU.
Massive multitask language understanding. It's a really challenging benchmark with thousands of multiple choice questions across a huge range of topics.
Like what?
College-level medicine, physics, astronomy, you name it. The lecture gives an example question about a Type 1a supernova.
Wow, that's pretty advanced.
It is. It really tests the model's breadth of knowledge.
And how do you evaluate the model on MMLU?
You see which answer choice the model assigns the highest probability to?
So you're not just looking for a yes or no answer.
Right. You're looking at the entire probability distribution over the possible answers.
Makes sense. But what about tasks where there isn't a single correct answer?
That's a much more challenging problem. Evaluating open-ended text generation is a whole other can of worms.
Right, because there's no objective way to say whether a generative story or poem is good or bad.
Exactly. It's very subjective.
And the lecture acknowledges that this is a complex topic that needs its own discussion.
It does. We'll probably need to dedicate a whole other deep dive to that.
Now, even with these benchmarks, there are still challenges in evaluating LLMs.
Oh, there are. The lecture points out a couple big ones.
What are they?
First, there's the issue of consistency.
Consistency.
Yeah. Even when using the same benchmark, different organizations might use different evaluation methods.
Which can lead to different scores for the same model.
Exactly. The lecture gives the example of Llama 65B, where the reported accuracy on MMLU varied significantly depending on who was doing the evaluation.
Wow, that's kind of concerning.
It is. It highlights the importance of transparency and standardization in evaluation.
So you know what you're comparing.
Exactly. What's the second challenge?
The lecture calls it train test contamination.
Which basically means that some of the data used to evaluate the model was actually present in its training data.
So it's like cheating on a test.
In a way, yeah. The model has already seen the answers, so it's not a fair evaluation.
And this can inflate the performance scores.
It can, and the lecture describes a clever trick to try and detect this. If the test examples were originally in a non-random order, you can check if the model is more likely to generate them in that order.
So if the model spits out the test examples in the exact same order they appeared in the training data, that's a red flag.
It is. It suggests that the model has memorized the data rather than actually learned the underlying patterns.
And this is more of a concern for academic research, right?
It is, because researchers often don't have complete control over the training data used by others.
But companies developing their own models usually know exactly what data they're using.
Right. So they can avoid this issue.
Okay, so we've talked about how we train these models and how we evaluate them.
Right, the two fundamental pillars.
Now let's talk about the fuel that powers the whole system. Data.
The most crucial ingredient.
And the lecture emphasizes that it's not as simple as just training on all of the internet.
Yeah, that's a huge oversimplification.
And even the concept of clean internet is pretty nebulous.
It is. The internet is a messy place.
Full of junk, spam, and all sorts of things you wouldn't want your model to learn from.
Exactly. So there's a lot of work involved in preparing data for pre-training.
What kind of work?
Well, the lecture outlines a whole pipeline of steps. It starts with downloading all of the internet.
Which sounds impossible.
It pretty much is. But there are organizations like Common Crawl that try to do it. They use web crawlers to collect billions of web pages.
Why?
We're talking about petabytes of data.
And they just download everything.
Pretty much. And the lecture shows an example of a random HTML page. It's messy.
Unfinished sentences, weird formatting.
All sorts of junk.
So that's the raw data.
Yeah. And the first step is text extraction,
Getting the actual text out of the HTML.
which can be tricky because you have to deal with all sorts of things like formatting tags, JavaScript code, and boilerplate content.
Boilerplate content.
Like headers, footers, navigation menus, stuff that's not really relevant to the language modeling task.
Right. You want to get rid of all that.
Exactly. And once you have the text, you have to filter it.
Filter it.
Yeah. You want to get rid of content that's not safe for work, harmful, or personally identifiable information.
Things that could bias the model or lead to inappropriate output.
Exactly. And this filtering often involves blacklists and machine learning classifiers.
So you're using AI to clean the data for AI.
That's right. And then there's deduplication.
Because the internet is full of duplicate content.
Tons of it. The same paragraphs copied across different websites.
So you have to identify and remove those duplicates.
Which is a huge computational challenge.
Especially at this scale.
Absolutely. And then there's heuristic filtering.
Heuristic filtering.
It means using rules of thumb to identify low-quality documents.
Like what kind of rules?
Things like outlier token distributions, strange word lengths, unusual document lengths, basically anything that looks fishy.
So you're trying to weed out the spam and the gibberish.
Exactly.
Yeah.
And there's even model-based filtering.
Model-based filtering.
You can actually use a machine learning model to help you filter the data.
How does that work?
Well, one approach is to use Wikipedia as a reference.
Because Wikipedia is generally considered to be high quality.
Right. So you can train a classifier to distinguish between web pages that are linked from Wikipedia and random web pages.
And then you use that classifier to prioritize the more Wikipedia-like content.
Exactly. You're basically using a smaller, curated data set to help you filter a much larger one.
That's pretty clever.
It is. And then there's domain classification and up-down weighting.
What does that mean?
It means categorizing the data into different domains.
Like news, fiction, code, and so on.
Right. And then you can adjust the influence of each domain during training.
So you might upweight code because it's good for reasoning.
Exactly. Or downweight entertainment content because it might not be as informative.
Interesting. And the lecture mentions that some organizations also do an end-of-training phase.
Where they fine-tune the model on a high-quality data set like Wikipedia.
So it's like a final polishing step.
Oh, exactly. It can help to improve the model's overall performance.
This is all so much more complex than I ever imagined.
It is. Data preparation is a huge part of LLM development. And someone in the audience asked about the data reduction ratio. Like, how much smaller does the data set get after all this filtering?
Right, because you're starting with petabytes of data.
The lecture doesn't give a precise number.
But it suggests that the overall effort dedicated to data preparation might be even larger than the actual model training.
Yeah, it's a huge undertaking.
And what about the team size? How many people are working on this?
It's hard to say for sure, but the lecture estimates that a substantial portion of a large AI research team would be involved in data-related roles.
Wow, that's a lot of people.
And remember, it's not just about the people. You also need massive computational resources to do all this data processing.
CPUs mainly, right?
For all the data manipulation and filtering.
And the lecture points out that getting the right data is still an open problem.
It is. Researchers are still working on more efficient processing techniques, better domain balancing strategies, and even using synthetic data.
Synthetic data.
Data that's generated artificially rather than collected from the real world.
Interesting.
And there's also the issue of copyright.
Oh, right. Because you're using data from all over the internet.
And some of that data might be copyrighted.
So it's a bit of a legal gray area.
It is. And companies tend to be very secretive about their data sources and preparation methods.
Makes sense. It's their competitive advantage.
Exactly. But the lecture does give us a sense of the scale of these data sets. They can range from hundreds of billions of tokens to tens of trillions of tokens.
Wow, that's mind-boggling.
It is. The pile, which is a widely used research data set, has around 280 billion tokens.
And where does that data come from?
All over the place. Academic archives, Wikipedia, Stack Exchange, GitHub, books.
And closed-source models like Llama 2 and 3 are estimated to be trained on trillions of tokens.
Right. And the estimated scale of GPT-4 is somewhere in that range as well.
This is all giving me a much deeper appreciation for the sheer amount of data that goes into training these models.
It's massive. And it leads us to another fascinating concept. Scaling laws.
Scaling laws, what are those?
They're one of the most surprising and important findings in the field of LLMs.
What do they find?
Around 2020, researchers discovered that for LLMs, bigger models and more data lead to better performance.
Okay, that makes intuitive sense.
But what's surprising is that this improvement continues without overfitting.
Overfitting.
It's a common problem in machine learning where the model learns the training data too well.
So it performs well on the training data, but poorly on new data.
Exactly. But with LLMs, that doesn't seem to happen.
So you can just keep making the models bigger and giving them more data?
And they'll keep getting better, host.
Yeah.